Yeah, so thank you for coming. I'm going to be giving a very brief talk about reinforcement learning, what the hell is it, and sort of what kind of problems it can solve. I'm also going to review some sort of recent successes of the technology and then some open questions and sort of what's left to do, which is a lot. So the talk is going to be very, very high level. If you actually have any knowledge about reinforcement learning, I have two things. One, I'm very sorry about what you're about to hear. And two, why are you not writing a NIPS paper right now? Good. So let's get started. First of all, what on earth is reinforcement learning? So to explain what on earth is reinforcement learning, I'm very quickly going to give a brief overview of what types of machine learning there are and how is reinforcement learning different. So there's basically three types of learning within machine learning. Unsupervised learning, in which you learn from unlabeled data, supervised learning, in which you learn from annotated examples, and reinforcement learning, in which you learn by trial and error. If you realize, that is actually 8 times the word learning in slide 3. So this is going well. Now let me explain that a bit more. So how does unsupervised learning kind of work? So first of all, we have a robot. So I'm going to be calling this the robot, the agent, the program, a bunch of names. So you're sitting there reading some form of data, which could be an audio, it could be text, it could be images, any sort of data, just looking through it. And then in a completely independent fashion, it comes up with something about it. So I think of unsupervised learning as sort of smart summary, right? Where you just give data and then the robot says something smart about it. In the same way as, so if you have an agent reading through internet forums, then it will be able to come up with something like a word cloud that tells you what are people talking about. So you don't need, so the agent doesn't need to know what basketball is to know that people in this forum talk mostly about basketball and not about cooking, that sort of thing. Then another kind of machine learning is supervised learning, which is similar, but in supervised learning you actually have to you need a human to tell the robot what it's looking at. So people, a common example that people give to explain what supervised learning is to train a machine to differentiate between cats and dogs. But this is the 21st century. That's way too easy. We're going to be distinguishing between Imperial spaceships and Rebel spaceships. So what you would do in a supervised learning setting is you give the machine a bucket with images and you say, well, all of these are Imperial spaceships, and you give it another bucket and you say, well, all of these are Rebel spaceships. And then you have a sort of a host of algorithms that will actually learn to differentiate between one and the other. Important thing, you need both the data, which is the images, and a label, which is typically provided by a human that says this is one or the other. So now comes reinforcement learning. Yeah, there we go. Good. So now comes reinforcement learning. So now what is reinforcement learning about? Reinforcement learning is mostly about problems that require a series of decisions once in a row, right? So as in when you play the game of Pac-Man, you not only have to take the right turn once, you actually have to make a series of decisions one after the other, and you have to get all of them right to win the game. So in the previous examples, if you get an image wrong, then, well, sorry, but that's still fine. Whereas in reinforcement learning, if you make a bad decision, then you could find yourself in a situation like this, where you're going to be eaten by a bunch of evil ghosts. And that is because in the past, you made a wrong decision. And those are reinforcement learning problems. So problems in which your robot can go and say, oh, bummer, I did something wrong. If you have that notion of regretting past decisions, then you're in a reinforcement learning problem, right? So it's not that reinforcement learning has any advantages or disadvantages with respect to the other two. It is solving a different kind of problem, the kind of problem that are games, for example. So, for example, let's go through some RL's. RL stands for reinforcement learning. Let's go through some of RL's greatest hits. So what have people actually done right in reinforcement learning in the last few years? I'm going to start with a number. That number is $1,766,250. So what is this number? This number is actually the amount of money that reinforcement learning program Libratus from Carnegie Mellon University made in a poker contest about 3 months ago. It's actually quite a bit of money. There's a big landmark in reinforcement learning research. Another one, a bit more sort of old school, was Deep Blue, which was a machine developed by IBM scientists and engineers. And this is actually the first time that a machine won a world champion, Garry Kasparov, in the game of chess. And there was also a huge thing in AI research and reinforcement learning. And then a more recent one that you may have heard of is AlphaGo, developed by Google DeepMind, again, scientists and engineers, that, similar to Deep Blue, it could beat Go world champion Lee Sedol in a game of Go. So those are huge landmarks that have shaped the status and the sort of trajectory of reinforcement learning over time. But you may be wondering, well, yeah, that's fine, but those are games, like, Go, chess, poker. I mean, those are really nice, but after all, they're games and video games. What useful things can you actually do with reinforcement learning, other than getting you bored by Google, which is in itself a pretty handy thing? What can we do with this? One thing you can do with reinforcement learning is robotic control. So you can actually, if you have a robot that has to move in the real world, then you can use reinforcement learning to obtain controllers or systems that will actually manage and control your robot in the real world. So it's actually very useful. You can also use this to make data center cooling systems. As a matter of fact, Google recently used very similar technology to save about 15% in their energy bill in their data centers, which is, if you're Google, a lot of money. Or you can also make talking machines. You can make dialogue systems for machines that talk with people and between them and then can share information, which is something which is, is a big step in bringing AI to our daily lives. Good. So now that I've given you this sort of teaser, there's so many amazing things that reinforcement learning can do. You'll probably be wondering, well, but how does it work? I need to know, right? So I'm going to go through a very smooth introductory description of reinforcement learning. It'll be very easy, very, very little amount of math involved. I'm not going to hurt you, but that's what I always tell them. Good, so in reinforcement learning, we start with a robot or an agent that is sitting there interacting with a potentially very challenging world or environment. And then the way it works is the following. The agent is reading or observing the state of the world. In turn, it can make actions. Again. Good. So in turn, it can make actions to influence its environment or its own state. And in return, it receives a reward, which is a signal of how well it's doing. So for example, if you're playing the game of Pac-Man, your reward would be how many points you get every time you move. And just for the purpose of sort of making this thing slightly more concise, I'm going to give them variable names. So actions are going to be called A, reward R, and state S, rather unsurprisingly. Good. So let's go and have a look at the game of Pac-Man, right? So this is a very classical example of a problem which you can apply reinforcement learning to. So in here, you have a screen which has a bunch of little diamonds that you want to go and collect because they give you a higher score. You have a bunch of ghosts which are evil and want to eat you. And then you have your own agent, which is you, the little Pac-Man there trying to bite up all the goals. So all possible configurations of the screen, including the positions of the goals, the ghosts, and the Pac-Man itself, those are possible states of your problem. And then you also have a series of actions you can take, which is you can basically move forward, turn right, turn left, or go back. So those are the actions and the states. And when we see that, when I was saying that the actions influence the state of the world, is because by moving there, you can actually influence where the ghosts are going to go to hunt you, or where are the diamonds, because you can just eat them up and gain score. Good. So I'm going to introduce a very important object in reinforcement learning, which is called a Q function. Q doesn't actually stand for anything. It is just a Q function. So what this thing is actually the sum of all the rewards we are going to get from now until the end of time, multiplied by a small discount factor. Let me quickly break this down for you. Don't get scared just yet. So this is basically, again, it's a sum of all the score you're going to get from now until the end of time, which means it could be, what are my chances of winning this game? Or how many, if I carry on doing what I'm doing now, how many diamonds or how many points do you think I can get? And this discount factor is typically a number that just says that you prefer to get the score now rather than later. So again, there's a very important thing that just tells you how desirable your state is, how much long-term benefit you can have by being in this state and doing this action. And then there's a really important equation in reinforcement learning, which is this. And this is all basically saying that the potential benefit that I can get now is the points that I'm getting at this time plus the maximum benefit I could possibly get at the next time. And this, again, looks all very mathsy and weird, but it's very intuitive. All the score that I'm going to get from now on is the score that I'm getting just now plus the score I'll get in the future. And this is a very, very important equation, so I'm going to put a very important light bulb on it. But because anthropogenic climate change is a real issue and we have to take immediate action, I'll replace it by a low energy consumption light bulb. And that is a really important equation there. Good, so now let's go back and see how this actually plays out. So again, we have our Pac-Man state and all these possible actions, and then our problem really is to decide which action is best to take now. So to do that, we can evaluate this Q function of this given state and this particular action. And this number, this thing is actually a number. It will tell me how good it is for me to be in this state and take this action right now. If that number is high, then you're generally in a good position. If that number is low, then you're generally in a bad position. That's all it's saying. And we can do this basically for all possible actions you could take, and then just pick the highest and go with that. So say that in this particular case, Pac-Man actually, you would prefer to keep going straight, because then you'll be able to go and eat that little white diamond. So if this number is highest, then you will go and, actually take this action over there. As simple as that. Now, let's say that, that's all fine. But now, of course, the problem you may be wondering is, well, where does this function Q come from? So this is actually learning this Q function. That's actually what we do when we see that, how do you train or how does a reinforcement learning system learn is actually by finding that Q function. So say that time goes through, and then you go from this state to that state. So you move about, ghosts move about, you eat a few diamonds and everything. So you go through this trajectory of sort of a bunch of states and a bunch of actions. Then, if you remember our really important equation with the light bulb, this is the really important thing, and actually training the system is very easy. You just make this update, and you're basically done. If you know a bit more about this, if you're a bit more technical, then you have to approximate this function, and of course, I'm only telling you a very, very partial story, but that's basically it. And then once you know this, then you can just run the whole thing and see your Pac-Man go in. Good, so that's all about it, except that we haven't actually said what this Q function is. And actually, one of the greatest things that have happened in reinforcement learning in the recent years is a big fusion between deep learning and reinforcement learning. So when this Q function becomes a deep neural network, then you have, you could have all sorts of weird hybrids, but actually this one worked. It was deep reinforcement learning. And if you want to see how big this thing is, actually, this is the Google trends for deep reinforcement learning, and it's been massively increasing over the recent years. This little spike over there is actually the date that DeepMind published their first Nature paper on deep reinforcement learning. So this thing is massively taking off, and we're just beginning to find out how massively useful it is. So it's probably not going to stop anytime soon. And actually, when I was making this slide, I said, oh, that's kind of funny. But what is the Google trends of Google Trends? And it's surprisingly unremarkable. It's basically just flat, except for this spike, which happens to be the US 2016 general election, for some reason. Good. So in deep reinforcement learning, actually what you have is you have this big, deep neural networks that people really like these days. And you basically just feed in the image of your game. You push it through all these layers of neurons and the whole of really computational things, and you end up with the Q values for each action. So if you remember this Q function we were talking before, it's basically just how good is it to do something at this point in time. So that is basically what reinforcement learning is about. You use a neural network to tell you how good it is to do something at this stage. And you do that, and with reinforcement learning, and this thing is tremendously powerful. So just as a quick sort of way to see this, could someone please click on the video? So there's a very classic video, thanks a bunch, which you may have seen already. There's a video of the first released deep reinforcement learning system released by DeepMind. I didn't do this myself, I wish. And it's sort of, as it starts learning, sort of becoming better at playing Breakout, it sort of starts getting the thing. By now, it mostly can pick the paddle, not always, but it's sort of getting there. As it keeps learning, it's actually very good at just catching the paddle. And so it plays as a human player would. Just go there, catch it, and do a little more. But surprisingly, as you keep this thing going, and by going, I mean actually letting your computer play against itself for weeks and weeks, then you start observing some really, really neat tricks. So again, this is all fully independent, right? This is the machine just playing against itself, and it realizes that you can do this sort of thing, where, yeah, why should I bother to actually move stuff around, right? I can just push the ball through and destroy this thing. This is fully independent, and this was a breakthrough. This was like, a few years ago, and this changed basically the state of the field. So that's what deep reinforcement learning can do on a really silly thing like Breakout, and we're way beyond that right now. But this is still a very visual and a very emblematic video. Good. So we're pretty close to the end of the talk. If you're interested in reinforcement learning, of course, this was a very broad introduction, but I would heavily recommend the book Reinforcement Learning, An Introduction by Rich Sutton and Andrew Bartow, which is free. It's fully available online, and it's an extraordinary book of reinforcement learning and general sort of AI. Is really good. If you're interested, take it, because it starts from very basic principles, and you shall not be disappointed. We done taking pictures? Yeah, take your time. Am I in the shot? Yeah, good. Yeah, good. All right. Yeah. So, more pictures. Oh, I can send you a link later if you're interested. Just give me a shout. Good. And then let's just very quickly finish with some open problems in reinforcement learning, because it's been all sort of nice and open, blue skies over here, but we're not done, basically. So what are the open problems in actually deploying reinforcement learning systems that work well and solve people's problems? One of them is that basically an agent needs to know what to do when it doesn't know what to do. So basically, there are some times in life where you really don't know if one thing is better than the other. So how do you make these decisions in the face of very little information? That is something that we're yet to solve in reinforcement learning. Another important problem to be solved is how can you learn quickly from new experience? So when you have a computer playing Pac-Man, you can really play as long as you want. It takes like milliseconds to run a game of Pac-Man. But if you have robots that are interacting in the real world with people in meat space, then actually it matters. Learning quickly matters, because there's risk of hurting people or damaging the robot, and you actually have to be very good at learning quickly. And another problem is, how do you know you learn the right thing? So if, say, that we deploy these systems in the wild, how do we, as programmers and designers, how do we know that they're doing what they're programmed to do, as opposed to, I don't know, maybe they can just find a backdoor to your sort of design or your program and start doing something else. So there's actually a very important problem that we're facing before we can safely deploy reinforcement learning systems in the wild. So that's as far as I'm going to go. Thanks to Cocoon Networks and Emotech for letting me open this thing. And please ping me if you have any questions. And let's go and have a look at Rasmus's talk on text-to-speech. Thank you very much.